So here we have a 75 kilogram personal size on a 5 meter water slide. It says dropping through a vertical height of 2.5 meters. It says if the person's speed at the bottom of the water slide is 6.2 meters per second. A, find out how much work does gravity do on the person. B, what is the net work done on the person. C, calculate the energy loss. And then D, find the magnitude of the average acceleration. All right, let's go and crack this up. So the first thing I like to do is define my x-axis. I will take my x-axis as the surface of the ramp, just because that's how the person in this particular problem is moving. So I'll take the line of motion to be my x-axis. But if you do that, you also have to make sure you draw your y-axis properly, which is perpendicular to the x-axis. Okay. But here, excuse me, in order to find the work due by the force of gravity, I need f of gx. The reason I need f of gx is because I need the component of f that's parallel to the displacement. So watch how I draw this up, okay? So here, f of g lies in between the y and x axis, which means it has to have components, f of gy and f of gx. But if you look at this particular diagram, the person is sliding down the surface of the ramp, which is what my cursor is doing. Well, if you take your arrow, or if you watch my cursor, excuse me, if you follow my cursor arrow, f of g is not parallel to that displacement. F of gy is not parallel to that. It's f of gx parallel to the surface here that I call x. So therefore, as you find work, it's important that you keep in mind you need the parallel component of the force that does the work along that same direction of the displacement. Okay, so in this case, the displacement is down the water slide, which means I need f of gx because it parallels x. All right, once you recognize that, it's super easy to do. Well, in order to do so, all you have to do is figure out this particular theta here. I do want to point out that the angle given this diagram touches the height. So therefore, it's a little different. Normally, the angle is given touching, the bottom of the ramp here to the horizontal axis. However, this diagram is a little different. The theta here given touches the height. So that's fine. Don't memorize cosine and sine. Just kind of, adapt and go with the flow. So here, because the angle that is given touches the height h and the slope or the water slide displacement, the same angle that just came up on my screen is also theta. Okay, so keep that in mind. Because typically, if you're given the theta that touches the water surface here and the ramp itself, if that's theta, then where my cursor is tracing, that's also the same theta. But because theta here is flip-flop, where you're given the angle that touches the y-axis, this is also flip-flop. So the theta here is given touching the f of gx and f of g. Well, here I'm just going to do cosine. Well, why cosine? Because for this particular angle, f of gx is the adjacent leg, and then f of g is the hypotenuse. So I will do cosine because I need f of gx, which is the adjacent leg. So by definition, cosine of theta is adjacent, which is f of gx, over hypotenuse, which is f of g. And if I were to solve f of gx, I would just multiply both sides, so f of g. So I have f of g cosine theta equals f of gx. Here, excuse me, I just carry my work down. Here, the work due to the force of gravity is f of gx times displacement. But f of gx, I can substitute out for f of g cosine theta because I just found that to be true. Delta x I choose to replace with d. If you want, you can keep it as delta x. But the diagram has the distance down the ramp or down the water side as d, so I just replace delta x with d. All right. Other than that, we can expand f of g out into mg cosine theta times d here. You know mass, you know g. Oh, you know d. D's 5. And then you actually don't know what theta is. But to find theta is super easy. So if you look at this particular diagram, the slope, right, is 5. The base, I don't know. But the height of the water side is given. And this angle touches the height of the ramp. So here, I can do cosine. Because by definition, when the cosine of this black theta that's given is adjacent over hypotenuse. So I'm going to do cosine of theta is equal to adjacent, which is h, divided by the hypotenuse, which is d. Well, to solve for h, to solve for theta, I know what h is. H is 2.5, To solve for theta, I just do inverse cosine of theta, which is 2.5 over 5, h being 2.5, d being 5. So therefore, if you punch this in your calculator, you'll get an angle of 60 degrees. Okay, so the angle up here is 60 degrees. So once I know that, I just plug everything in. Mass is 75, g is 9.8, and then cosine of theta of 60, and then d being 5 meters, and then all this on your calculator will give you 1837.5 joules. So that's our answer for part A. What I do want to point out is this big misconception oftentimes, okay? Oftentimes, folks, when you're asked to find how much work does gravity do on a person, because it says, gravity, folks might just do FG times D. But if you look at the diagram, FG is pointing down the page, the surface of the ramp is pointing down slope, and those two vectors are not, they're not parallel. So when you do work in physics, you have to make sure that you do the dot product, right? And these two things have to be parallel. Hence, earlier I used f of gx because f of gx parallel delta x, okay? So this is so this is a big no-no, okay? You cannot just take f of g times d just because, it says find the work done by gravity. Make sure things are parallel. All right. But other than that, if you kept up with my work earlier, here it says WFG equals mg cosine theta times d. I like to point out that the work due by gravity is the same as the potential energy stored in the system initially. So watch my work. Okay. Here, I just carry the work down here where it says WF of G is equal to mg cosine theta times d. But you notice here in my work now, I group cosine theta and d together in parentheses. Well, why? Because if you look at my cursor, I made a statement earlier that says cosine theta is equal to h over d, right? Well, here, I can find what h is by simply multiplying both sides by d. So, I can say that d times cosine theta is equal to h. But what I just circle down here is cosine theta times d, which is the same as d times cosine theta, because when you're multiplying, the order of the variable doesn't matter, right? So cosine theta times d, which is the same as d cosine theta, can be now we substitute out for h. So here we have mgh. So if you plug in, mass being 75, g being 9.8, then the initial height being 2.5, you actually will get the same answer as the previous strategy that did, which is 1,837.5 joules. Okay, let's move to part B. Part B asks you to find the network. Well, to find the network, I think the easiest way to do it is just using the work kinetic energy theorem. So, which states that the net work on the system is just a change in kinetic energy. Here, I can break delta KE into KF minus KI because that's what delta KE is. I can cross out KI because KI is 0 because the person starts at rest. And then KF can be broken down into 1/2 mv squared. Well, M is given as 75. VF at the bottom of the water side is given as 6.2. So, I can just plug and chug. Okay, so therefore it's 1/2 times 75 times 6.2 squared. And if you do that, you'll get about 1,441.5 joules. And that's the answer for part B. All right, let's go ahead and move on to C. In order to calculate energy loss in this particular problem, you have to do the initial mechanical energy minus the energy loss equals to how much is left over at the very bottom. So I'm just going to expand this function. Well, MEI is just PEI plus KEI minus E loss because, again, it's energy loss, so you have to take it away from the system. And then MEF is just KEF plus KEI. Here I'm going to cross out a couple things because KI is 0. KI is 0 because the person starts at rest. And then PF is 0 because I want to treat the bottom of the slope as the lowest point, which means there's no height. From here, I can solve for KE loss by moving it to the right side of the function because that's what I'm trying to find in part C. And then I want to move this positive KEF to the left side. So here I have PI minus KEF, which is equal to E loss. And then I'm just going to do a little plug and chuck here. PI is just mghi minus 1/2 mvf squared. That equals E loss. And then here mass is 75, G is 9.8, HI being 2.5, which is given in the diagram. And then 1/2 M, which is 75, and then the VF at the bottom, 6.2, square that. I left out the units because I'm running out of space on the screen here. And if you simplify this, the first term will give you 1,837.5 joules, and the second term will give you 1,441.5 joules here. All right. So therefore, if you do this, the energy loss is 396 joules, and that's our answer for part C. And then last but not least, to find part D, it says find the magnitude of the average acceleration. I'm just going to go back to my kinematics days. Here, VF crosses out. Excuse me, VI crosses out. It starts at 0. I'm trying to find A, but I know VF 6.2. So, I'm just going to clean this up a little bit. So, VF squared equals 2A delta X. To solve for A, I'm going to divide both sides by 2 and delta X. Here, VF is 6.2. I want to square that, and then 2, and then delta x here being 5, and then therefore if you post it in the calculator, you should get a magnitude of about 3.84 meters per second squared. Okay, and that is our answer for part D. All right, I hope that helps. Sorry for the coughing. Stay nerdy, and we back.